Welcome to this module. In the last module what we have seen is the effect of the input offset voltage, right. So, and earlier input offset current, and before that we have seen input bias current. In this class we will see what are the few more characteristics of operational amplifier such as thermal drift. So, what exactly is the thermal drift? So, let us see the slide. Thermal drift, being a semiconductor devices, op amps are subject to slight changes in behavior which changes in the operating temperature, that we know, right, because op amps are made up out of semiconductor devices. So, op amps are considered as semiconductor devices because we are using semiconductor material to design the op amp, and when you are using semiconductor material it has it will change, it will slightly change its behavior with change in the operating temperature. So, a circuit nulled at 25 degree may not remain so when the temperature rises to 35 degree. This is called the drift, this is called the drift. Bias current, offset voltage change with temperature, alright. So, we have to understand that at different temperature, if you have nulled for one temperature, it may not be nulled for another temperature, okay. The drift parameters can be specified for the bias current, offset voltage and the like. The manufacturer data sheet specifies the quantity of any particular op amp. It tells about the amount of input offset changes with each degree of centigrade change in the temperature, right. Now, for LM741 the worst case drift is 15 microvolts per degree centigrade. This is a worst case drift. So, if the circuit has to be operated from 0 to 60 degree, the input could change by 15 microvolts per degree centigrade into 60 degree, which is 0.9 volts over 60 degree temperature range. That means, from 0 to 60 there is a change of 0.9 millivolts, right. So, it is very important to understand the thermal drift, at what temperature you are nullifying your output voltage. Now, let us see an example. A non-inverting amplifier with a gain of 100 is nulled at 25 degree. What will happen? What will happen to the output voltage if the temperature rises to 50 degree for an offset drift of 0.15 millivolts per degree centigrade? This is a given problem, right. This is a given problem. What is the problem? That if a non-inverting amplifier is there and it has a gain of 100 and is nulled at 25 degree centigrade. So, our output voltage is 0, right, everything is taken care of. But what happens to the output voltage if the temperature rises to 50 degree, almost double to this, right, double to 25, for an offset voltage drift of 0.15 millivolts per degree centigrade, right. Let us see, input voltage due to temperature rise is 0.15 by degree centigrade into 50 minus 25, which is 25, which is equals to 3.75 millivolts. Since this is an input change, the output voltage will change by VO equals to VOS into gain, which is nothing but VOS is 3.75 into open loop gain or closed loop gain CACL is nothing but 375 millivolts. So, our output voltage VO will be equal to 375 millivolts. This could be represent a very major shift in the output voltage, right, because this is the change in the output voltage, this is a very major drift. So, that means that there is significant effect of temperature on the performance of the operational amplifier. Let us see some more parameters, some more characteristics. Another characteristics is input impedance. The impedance in looking into the input pins is input impedance. LM741 has a minimum input impedance of 2 mega ohms. Note that this is considered low. Many op amps have input impedance over 1 giga ohms. Okay. Now, input voltage range, how high or low voltage the input pins can be applied before op amp does not function properly. That is called input offset voltage range, right. Does not function properly means it will get damaged. In this case, assuming plus minus 15 volts apply, the input should stay below plus minus 13 volts, right. This is in general, okay. We are talking about in general. If I apply plus minus 15, my input voltage range should be around plus minus 13 volts. Large signal voltage gain, the gain of the op amp at DC, right. Earlier we stated that the gain was infinite. In real world it is large, but not infinite. Typical the gain is about 200 volts per millivolt or 200,000, right. Now, output voltage swing, the output voltage swing, how we can define? The output can swing all the way to the power supply rails, right. It cannot go all the way to plus 15, minus 15 or whatever power supply we have given. The maximum output voltage also depends on the load current, right. With a smaller load, the output can go higher than with a larger load, right. Most of the op amps can swing output to within a few volts to power supply rails. That means that there are special op amps called rail to rail op amps that can swing the output within 100 millivolts. These special op amps are often used in battery operated products where the power supply may be 6 volts or less. Got it? That is what your output voltage swing. Let us see another parameter, which is output short circuit current. What is that? How much current that op amp can source or sink from the output pin. The output voltage could drop near 0 volts when delivering the maximum current. Typically, the op amp cannot deliver more than 25 milliampere. Okay. Then we have seen our favorite common mode rejection ratio. We know that the ratio of the difference gain to the common mode gain, AD by ACM, is our common mode rejection ratio. Op amps are only supposed to amplify the difference and of the inputs and not the common mode gain, but in reality there is a common mode voltage, there will be a small gain even though the inputs are same. The CMRR tells how good the op amp is minimizing this common mode gain. 741 has a worst case of CMRR of 70 dB and typically it is 90 dB, that is 300,000. However, some instrumentation and difference amplifier has CMRR over 300,000. Okay. This is 30,000, right. This is 30,000 for LM741, but in case of some of the amplifiers, some of the instrumentation and difference amplifier, this is about 300,000. That is really great. CMRR high, our output will be close to AD into VD. We have seen the problems earlier when we were looking at CMRR, right. We have solved the problems. Now, let us see what is power supply rejection ratio. Okay. It is called PSRR. If you know, we in the data sheet there was a power supply rejection ratio. The power supply voltage rejection ratio is nothing but it will tell about how well the op amp filters out the noise coming through the power pins, right. There is a noise generated in the power pins also. So, for example, a 12 volt supply with 100 millivolt of ripple at 120 hertz, how this effect of the op amp circuit, how this will affect on the op amp circuit. We have PSRR of 96 dB, we will have was 63,000. So, the ripple seen by the input will be reduced by factor of 63,000. So, with a 100 millivolts ripple and a PSRR of 96 dB, the op amp input would see a ripple of 1.6 microvolts, right. Therefore, a gain of 100, the output will have ripple of 160 microvolts even when there is no input to the op amp. This is why it is required to filter power supply well and to have a good PSRR. You understand? So, in most of the circuit you will say that you have to use power supply which is having a very good power supply voltage rejection ratio, so that the noise coming through power supply is taken care of, right. And it is generally usually specified at 120 hertz, but it drops at the higher frequency. This is about the power supply voltage rejection ratio. What is transient response? Transient response is nothing but this gives you an idea of how fast the op amp will respond to the pulse input, right. There is a transient response. That means that rise time may be the time it takes from signal to go from 10% to 90%. How fast when I change, let us say this is a op amp, if I apply the input, right, at the time of the input that I apply, how fast I see the change in the output, right, is a lag of 10 seconds, lag of 1 second, lag of few milliseconds, that is your transient response, that is your transient response, right. So, with this I should be continuously able to see the change in the output voltage if the transient response is faster. So, let us see few more things. One is called slew rate. What exactly slew rate is? How fast the op amp can change, and it is measured in volts per microseconds, right. This will give you an idea of maximum frequency and amplitude signal the output can handle without distortion, right. In case of 741, LM741, the typical slew rate is between about 0.5 volts per microsecond, right. So, if you have a 10 kilohertz 10 volt peak to peak sine wave, right, on the output the fastest point at which the voltage changes it as the 0 crossing, the rate of change dV by dt is nothing but 0.63 volts per microsecond. So, since 0.63 volts per microsecond is about the typical value of 0.5 volts specification, right, in the data sheet, there is a good chance that 10 volts peak to peak sine wave will have a distortion at 0 crossings. To operate the without distortion, the way is to lower the voltage or lower the frequency. You got it. So, if my output is 0.63 volts per microsecond, but my specification says that my slew rate should be 0.5 microsecond volts per microsecond, then there is a possibility that there will be distortion at the crossing of at the 0 crossing, and to operate the op amp without any distortion, what we require is to lower the voltage and lower the frequency. Again, LM741 is considered as low op amp. You can get an op amp with a slew rate excess of 1 volts per nanosecond. Alright. Let us see the next one, bandwidth or gain bandwidth product, very important characteristics of an op amp. The gain as a function of frequency for smaller signals, right, that is output is unlimited by slew rate. The LM741 has a gain bandwidth product of 1 megahertz. Okay. This means that with a 1 megahertz input maximum gain is 1. But actually this gain is less than 1 because gain bandwidth product is defined as 3 dB decibel point, 3 dB point, right. We have already seen what is 3 dB, or that is where the voltage drops about 0.707 of its original value, right. We have seen that if the input signal was 100 kilohertz, the maximum gain would be 10, where it is 10 kilohertz, the input maximum gain would be 100, right. So, this is about your bandwidth or gain bandwidth product. Supply current, the current drawn from the power supply when no load on the op amp is called your there is a current that is drawn when there is no load to the op amp. Okay. So, this is your supply current. There are lower op amps available that run on less than 10 microampere. Usually the faster op amp runs on more power. It is obvious. It is obvious. So, when you see these are the some of the parameter that we were looking at in the data sheet. So, if we quickly go back and see that what exactly were the parameters in data sheet, then it will be that we will see that okay, the data sheets that we were looking at, whether now looking at these parameters, understanding the characteristics, whether it makes sense to go back and see whether we are understanding the parameters or characteristics given in the data sheet. So, let us quickly see once again what are the parameters or the characteristics given in the data sheet of LM741, and we will end up this particular module. Alright. So, let us see the slide once again. Here what you see is if you go to the characteristics, supply voltage we have seen this, output circuit duration we have seen, power dissipation, temperature range. Okay. Now, if you see here input offset voltage, now we know, right, how we can compensate the effect of input offset voltage. We can compensate the effect of offset current, we compensate the effect of bias current, what is input resistance, what is input voltage range, what is output short circuit current, what is voltage swing, what is common mode rejection ratio, what is power supply rejection ratio, right, what is slew rate, what is bandwidth, what is the power consumption, what is the supply current. Now, we can see everything we have seen in the slides, right, we have seen everything in the slides. Same way input offset voltage, voltage drift, right, CMRR, we have seen CMRR, we have seen power supply rejection ratio, output short circuit current. Now, for a given data sheet, you guys would be able to understand how the things work, right. That was the idea, that at least some of the parameters on the data sheet, when you open the data sheet you will be able to know. At the same time, what are the ordering information for that particular IC is also given in the data sheet. So, what we have seen until now, we have seen how the data sheet, when we open the data sheet, what are the parameters or characteristics given in the data sheet, and can we understand how to use these characteristics for our for compensating our output, right, for getting our output to be 0 or to make the output null, right. So, we have to understand how we can deal with input bias current, input offset voltage, input offset current, right. We have to understand how we can nullify the output voltage when both the terminals at the input are ground. We have to understand how the change in the output voltage would happen even the offset is nulled at particular temperature if I change the temperature, right. We have to understand how the plots or how the frequency will affect the overall performance, right. So, there are a lot of things to understand, lot of things to learn, and we have taken few things from that lot to understand this particular amplifier called operational amplifier, right. So, I hope that if you go through the entire series of lectures for this particular course, for this particular theory class, then you will know how the things works, particularly in the area of operational amplifiers, how you will know how the things works when you are given a indicator circuit, and if you are asked that what are the process flow or how you can fabricate a indicator circuit or an indicator circuit or a device, you will be able to at least tell that okay, we know how the process flow works, we know how we can grow silicon dioxide, we know how we can deposit a metal, we know how we can do lithography, we know how a MOSFET is fabricated, we can fabricate N channel, we can fabricate a P channel, we know the depletion MOSFET, we know enhancement MOSFET, we know the application of MOSFETs, right, its drain characteristics, we know the transfer characteristics, we know the current mirror, we know how CMOS works at least as a NOT gate, right. So, lot of things if you really think we have tried to cover in this short duration of 30 hours. Apart from this theory, like I said, we will also do few experiments so that you get the idea of how to use the circuit and how to perform experiments, so that we also understand that how the theory is there, we will do some simulations and we will do some experiments on the breadboard, right. With that I will see you in the next class. Till then, you take care.